Time. It never stops, never waits. You blink a year has passed. You turn around, your childhood is gone. And yet, remember when you were small? An afternoon felt like forever. Summer stretched like an eternity. But now, the same stretch of time evaporates in an instant. Why? Why does time move fast when we want it slow, and crawl when we wish it would fly? Here's the unsettling part. Maybe time doesn't move at all. Maybe movement is just the illusion. What if the flow of time, this constant current we all believe in, was never real to begin with? What if time is a trick your brain plays on itself? Now imagine this. You wake up, it's morning, your alarm blares. You reach for your phone. The numbers count backwards. 7, 6, 5, 4, or this. You eat dinner, watch a show, go to bed. Next morning, it's the same day. Not just déjà vu, the day has repeated perfectly. You are stuck in a loop. Impossible? Maybe, but maybe not as impossible as you think, because time, the most obvious thing in our lives, is anything but simple. We measure it, we schedule by it, we race against it. But ask a physicist what time really is, and you'll see hesitation in their eyes. The truth is, no one agrees. Some say time is absolute, some say it's relative, some say it's emergent, others say it's an illusion altogether. And in the middle of that chaos is you, the person just trying to make sense of morning and night, of clocks and calendars, of memories and hopes. In the next few minutes, we're going to walk a winding path together. We'll start small. Why does time feel so strange? Why does waiting in line feel longer than watching a movie, even if they both lasted exactly 60 minutes? Then we'll zoom out. We'll step through the story of how humans measured time, from shadows cast by ancient stones to atomic pulses bouncing in space. Then we'll break open the physics. You'll meet Newton, who thought time was a ticking, invisible drumbeat, and Einstein, who shattered that rhythm with a thought experiment on a moving train, and quantum physicists who believe that time might not exist at all. You'll fall into black holes, fly with GPS satellites, and step into paradoxes where the future might affect the past. We'll explore entropy, the arrow of time, and how the universe might be slowly forgetting its own beginning. And finally, we'll ask the deepest question: if time is not real, then what is real? And if the future already exists, do we even have a choice? By the end, you may never look at a clock the same way again. But let's not rush ahead. Let's begin at the only place we can truly feel time: your mind. Have you ever been in danger? A car swerves. Your hands grip the wheel. Your heart thuds. And in that moment, time slows down. Everything seems to stretch. You remember every detail. Why? Because your brain enters emergency mode. It soaks in information, processes it faster, burns the memory into your mind. Later, when you look back, that moment feels longer, not because time changed, but because you changed. Psychologists call it the memory density effect. The more intense the moment, the more data your brain records. And the more it records, the longer that moment seems. That's why your childhood felt long. Everything was new. Everything mattered. Your brain stored more. But now, most days blur together. Routine erases novelty. Memory compresses time. That's also why time seems to move faster as you age. It's not your body changing. It's your perception collapsing. Our experience of time, it turns out, is not objective. It's deeply tied to how we feel, what we notice, how often we stop to breathe. Even anxiety warps it. Ever check the time while waiting for someone? Minutes stretch like hours, but scroll through your phone for the same amount of time, and it vanishes. In flow states, those rare moments when we're fully immersed, time evaporates. We lose track. We merge with the now. So already, we're seeing it. Time isn't just a clock on the wall. It's a shifting canvas of sensation. Even in science, time is slippery. Because here's a question: if you had no memories and no way to measure change, would you still believe in time? Without events, without a sequence, What is left? This is where we begin our journey. Because if the way we feel time is this distorted, what about the way we measure it? What even is a second? Why are there 60 of them in a minute, 60 minutes in an hour, 24 hours in a day? Why does the calendar jump in odd months, 30 days, 31, 28? Who decided? And what if time, the fixed backdrop to your life, was just a human invention? A story we told ourselves to keep from drowning in the unknown? This story starts thousands of years ago with shadows and sun, but we'll get there in a moment. For now, all you need to know is this: time is not what it seems, and once you see it clearly, you'll never unsee it again. So if time feels different depending on your mood, your memories, and your attention, then how do we standardize it? How did we go from individual, messy sensations of time to a world synchronized down to the nanosecond? Let's rewind not with machines, but with sunlight. Thousands of years ago, humans noticed something curious. Shadows moved. A stick in the ground cast its shadow across the dirt, and that shadow crept ever so slowly. It wasn't random, it was predictable, a kind of cosmic metronome. That was our first timekeeper, the sun. The sundial was born, not a machine, but a reflection of the earth turning. But there was a deeper curiosity too. Ancient Babylonians more than 4,000 years ago divided the sky into arcs. They had a thing for the number 60. Why? Because 60 is divisible by so many numbers: 2, 3, 4, 5, 6. It made calculations cleaner, more civilized. So time, like math, became structured. That's where we got our hours, minutes, and seconds. 12 hours of daylight, 12 of darkness, 60 minutes, 60 seconds, all decided long before you were born, by people watching stars, counting moons, carving tablets. But sundials don't work at night. They don't work on cloudy days. They don't work indoors. So we turn to water. In China, Egypt, Mesopotamia cultures invented clepsydras, bowls with holes that leaked water at a constant rate. As the bowl drained, time passed. When it was empty, that was your alarm. But water had problems. It evaporated. It froze. It was never perfectly constant. Next came candles, tall wax sticks marked with rings. As the flame burned downward, each ring melted a crude countdown. And then came gears. In medieval Europe, the mechanical clock emerged. Weights, pendulums, escapements. Now, for the first time, humans could measure time without relying on the sky. They could place time indoors. They could tell time in any weather. It was revolutionary, and it changed how we worked, traveled, and thought. Soon, time wasn't just something we watched, it was something we obeyed. The Industrial Revolution tightened the screws. Trains needed schedules. Factories needed shifts. People needed clocks that didn't drift. In a world of machines, time became a machine too. But then came a problem no gear could solve. Imagine this. You're a sailor in the 1700s. Your ship is lost at sea. You can calculate latitude by the sun's angle. But longitude? That's tricky. To know your longitude, you must know the exact time at a reference point like Greenwich. But clocks of the day made with pendulums didn't work on rocking ships. Enter John Harrison, a carpenter, not a scientist, but a man obsessed. He spent decades crafting the perfect clock, one that wouldn't be rattled by waves, wouldn't seize in salt air, wouldn't drift in temperature. He succeeded. His marine chronometer changed everything. It won the famous Longitude Prize, and it made the oceans and the world more navigable. Fast forward to the 20th century. Our quest for perfect time didn't stop. Scientists discovered that certain atoms, like cesium, vibrate at a precise frequency, and, unlike a pendulum or a gear, this vibration was unshakable, unchanging, universal. In 1955, the first atomic clock was built. Suddenly, we could measure a second not as a fraction of a day, but as 9,192,631,767 70 vibrations of cesium. That's what defines 1 second today. Not the sun, not the shadow, not a ticking hand, but the pulse of a single atom, and it matters more than you might think. Because up above you, floating in orbit, are dozens of satellites. They make GPS work. But here's the twist. GPS wouldn't work without Einstein. Why? Because those satellites traveling fast and far from Earth's gravity experience time differently. Special relativity. Motion slows time. General relativity. Gravity bends time. If engineers didn't adjust the clocks on those satellites, your GPS would be off by miles within a single day. So that walk you took in the park, that route to work, that map on your phone, it only exists because we understand time, not just as something we feel, but something the universe itself distorts. Time isn't universal. It isn't absolute. It's not even constant. It shifts, it bends, it stretches, and yet we still use it like it's solid, putting it into calendars, clocks, and countdowns. But now you know what feels simple is anything but. The next time you check your watch, remember the atoms vibrating, the satellites adjusting, the centuries of thinkers, tinkerers, dreamers, and engineers who made that moment possible. But there's one more layer, because while we've learned how to measure time, we haven't agreed on what it is. Now it's time to meet the people who shaped that question. Isaac Newton, Albert Einstein, and the physicists who followed. In the next chapter, we'll step into a world where time is a river, a fabric, a dimension that warps and twists, and may not exist at all. Hold on. Everything you think you know about past, present, and future is about to break. You've now seen how humans learned to track time from sundials to satellite clocks. But here's the deeper question. What is time when we're not measuring it? What is it, really? To find that answer, we need to go back over 300 years, to a world ruled by certainty. The world of Isaac Newton. He saw the universe as a machine, elegant, orderly, precise, a vast celestial clock, and in this machine, time was absolute. It ticked forward, everywhere, at the same pace, steady and unchanging, like a drumbeat that echoed across the cosmos. You could travel to the other side of the galaxy, and that same second would still be ticking there, just as it is here. Newton believed time flowed independently of everything else. It didn't care about motion. It didn't bend for gravity. It simply was. In his view, the universe ran on rules, and if you knew all the positions and velocities of every object at a given moment, you could predict the entire future. Every collision, every orbit, every falling apple, even you, your thoughts, your choices, your dreams, could be predicted. This wasn't just science, it was philosophy. It led to what's now called Laplace's demon. Imagine a super intelligent being that knows everything about the universe right now, every atom, every particle. With that knowledge, it could calculate everything that ever happened and everything that ever will happen. No mystery, no randomness, just cold, hard logic. It's a beautiful idea and a terrifying one, because in Newton's clockwork universe, there's no room for true freedom, no room for free will. You might feel like you're choosing, but really, you're just a cog in a vast, unfolding machine, set into motion at the beginning of time. Every decision you make was already baked into the initial conditions of the universe. That raises a heavy question. If time is a perfectly ordered script, are we just actors reading our lines? Are we just passengers, watching a film we cannot pause or rewrite? It's a seductive idea, this vision of perfect predictability. But cracks would soon appear, and the first one had to do with light. For centuries, people assumed that light needed something to travel through, a medium like air or water. And just as sound needs air to carry its waves, they believed light needed the ether. This invisible, all-pervasive substance was thought to fill the universe, acting as a canvas on which light could ripple. It made perfect sense, at least on paper. But how do you test it? Enter the Michelson-Morley experiment, one of the most important null results in history. In the late 1800s, two physicists set out to detect the aether. They figured if Earth moves through this invisible medium, then light should appear to move at slightly different speeds depending on direction, like a swimmer going with or against the current. So they built a device part telescope, part mirror maze, placed it on a floating stone slab, so it could rotate freely. They shot beams of light in perpendicular directions and recombined them to look for interference, a kind of optical fingerprint that would reveal motion through the ether. They waited, they rotated, they measured, and they found nothing. No difference, no interference, no ether wind. The experiment failed, but in that failure, something profound was revealed. Light didn't care about direction. Its speed was always the same. And if light's speed is constant, no matter how you move, then something else must be wrong. Newton's picture of absolute time and space was beginning to unravel, but no one knew what could replace it. Not yet. It would take a patent clerk in Switzerland, a young man with strange ideas and little formal training, to crack the puzzle open. His name was Albert Einstein, and in just a few short years, he would turn the concept of time from a river that flows through the universe into something far more strange. But before we meet him, let's pause. Let's return to the world before relativity. Because in Newton's universe, the laws are pristine, the math is perfect, and time is sacred. To many, it was comforting. In a chaotic world, here was a framework of logic, a belief that everything had a reason, a rule, a cause, and yet, even in Newton's time, not everyone was convinced. Some asked, if time is so absolute, why can't we see it? Why can't we touch it? Why is it only ever marked by change? A ticking clock, a falling leaf, a growing child, time itself remains invisible, like the wind, felt, but never seen. And that raises a deeper question. Does time exist independently of things happening? Or is it just a measure of change, a way we count the transformations around us? In Newton's framework, time exists on its own, but that assumption would soon be shattered, because once Einstein enters the story, everything we just said will flip upside down. The idea of simultaneity, that events happen at the same time for everyone, will dissolve. The notion of absolute motion, gone. Even the flow of time itself will become relative. So take a breath. The clock is about to break, and what we'll find in its ruins is more beautiful, more haunting, and more real than anything Newton ever imagined. It was 1905. In a small office in Switzerland, a 26-year-old patent clerk sat thinking, not about patents, about light. His name was Albert Einstein, and he didn't yet hold a PhD. He wasn't a professor, he had no laboratory, but he had a mind that would change the universe. And he started with one simple, strange idea. The speed of light is the same for everyone, always, everywhere, no exceptions. It sounds innocent, but it breaks everything Newton ever taught us. Because if light always moves at the same speed, even when you're moving toward it or away from it, then time itself can no longer be absolute. Let's try a thought experiment. You're standing still, you shine a flashlight. The beam travels at about 300 million meters per second. Now imagine you're in a spaceship, flying forward, and you shine the same flashlight. Intuitively, you'd expect the beam to move faster now. Your motion should add to the light's speed, like throwing a ball while running. But it doesn't. In both cases, standing still or flying, the light travels at the exact same speed. This is not a quirk. It is a rule, a universal constant. So, how does the universe make that true? By changing everything else. If the speed of light stays the same, then distance must stretch, time must slow, and simultaneity, the idea that now is the same for everyone, must vanish. This was the birth of special relativity. Einstein's theory had two assumptions. First, the laws of physics are the same in every non-accelerating frame. Second, the speed of light is always constant, no matter the motion of the source or observer. Together, these ideas force the universe into strange shapes. Clocks moving at high speed tick slower. Distances moving at high speed appear contracted, and events that are now for you may be in the past or future for someone else. Time is no longer a river, it's a fabric, a malleable thing, stretched and twisted by motion. Let's see how far that goes. Imagine this. You have an identical twin. One day, they climb aboard a spaceship and fly away at near light speed. You stay on Earth. To your twin, only a few years pass during the trip, but to you, back home decades go by. When they return, you've aged 40 years. They've aged only 4. You're now an old man. They're still young. That is not science fiction. That is reality, predicted by special relativity. It's called the twin paradox. But wait, you might ask, isn't motion relative? Can't the twin on the spaceship claim you're the one moving? Yes, but only to a point. The symmetry breaks when one twin accelerates, turns around, decelerates, and returns. That acceleration defines a preferred frame. It distinguishes who stayed still and who changed frames. So the paradox isn't a paradox. It's a real, testable outcome. And we've tested it. In 1971, physicists Hafele and Keating boarded commercial airplanes carrying atomic clocks. One flew east, the other flew west. They compared the time on these flying clocks to clocks on the ground. And sure enough, the airborne clocks ticked slightly slower, just as Einstein predicted. The effect was small, mere billionths of a second, but it was real and measurable. We see the same thing every single day in GPS. Satellites orbit Earth at high speed and higher altitude. That means they experience 2 relativistic effects. First, special relativity. They're moving fast, so their clocks tick slower. Second, general relativity. They're farther from Earth's gravity, so their clocks tick faster. Those effects don't cancel. They add up to a net gain of about 38 microseconds per day. That may seem trivial, but if left uncorrected, it would throw off your GPS location by several miles in just 24 hours. So, engineers compensate for it. Einstein's equations are literally embedded in your phone. Every time you use a map, order food, or navigate to a friend's house, it's one thing to say, relativity is weird. It's another to realize that your daily life depends on it working. But here's where it gets even stranger. In the relativistic view, there's no such thing as a universal now. Events don't unfold in a single cosmic order. They unfold in different orders, depending on how you're moving. 2 explosions that seem simultaneous to you may happen at different times to someone zipping by at half the speed of light. And this is not just about perception. It's not a trick of your senses. It's baked into space-time itself. Time is relative. Simultaneity is relative. There is no absolute present. We live in a world without a shared now. And yet, we function. We build cities. We send rockets to Mars. We fall in love, celebrate birthdays, mourn losses, all within a reality where time is both essential and fundamentally subjective. So what is time, really? Is it a flow, a coordinate, a perception, or just a label we stick onto events to make sense of a deeper, timeless structure? Einstein had more to say on that, because what we've seen so far is only half the story. Special relativity bends time with motion, but his next theory, general relativity, would show how gravity itself can bend time, warp space, and curve the very fabric of the cosmos. Next, we fall into black holes. We ride the arc of warped spacetime, and we begin to ask, does time ever really end? Motion slows time. That was Einstein's first great shock. But his second idea was even more profound. What if gravity does the same? What if gravity doesn't just pull on matter, but pulls on time? To understand this, we need to abandon the Newtonian idea of gravity as a force. Forget apples falling, planets orbiting, and invisible attractions. Think instead in terms of geometry. Here's the key insight. Mass tells space how to curve. Curved space tells objects how to move. And when time is part of space, then gravity curves time as well. Welcome to general relativity. Imagine a rubber sheet stretched tight. Place a heavy ball in the center, it creates a dip. Now roll a marble nearby. It spirals inward, drawn not by a force, but by the curve in the surface beneath it. This is how Einstein reimagined the universe. The sun doesn't pull Earth, it bends the space-time around it, and Earth moves along that curve, like a marble circling a funnel. Even light, which has no mass, follows these curves. In fact, one of the first proofs of general relativity was the way starlight bends as it passes near the sun, confirmed during a solar eclipse in 1919. But here's the twist. Because time is woven into this fabric, it bends too. The stronger the gravity, the slower time flows. Clocks tick more slowly near massive objects. This is not theory, it's measured fact. Consider this. You place two atomic clocks, one on a mountain, one in a valley. After a while, you compare them. The one in the valley, closer to Earth's center, deeper in the gravitational well, ticks more slowly, by an absurdly tiny amount, billionths of a second per day, but enough to matter. Your phone's GPS, for example, must account for this. Satellites farther from Earth feel less gravity, so their clocks tick faster than clocks on the ground. Without correcting for this difference, your location data would quickly become useless. Einstein's equations quietly shape your everyday life. But it goes further still. Let's say you fall toward a black hole, the most extreme gravity well we know. To someone watching from far away, your time slows. You descend toward the event horizon, the point of no return, and your motion seems to freeze. You never quite cross it. You appear locked in time, suspended forever, just outside. But to you, the falling traveler, time feels perfectly normal. You fall through the horizon, into the darkness. No dramatic pause, no freezing, just silence. This paradox of time, both freezing and flowing, is not science fiction. It is relativity, playing out on the grandest scale. The event horizon marks the boundary where gravity's grip on time becomes absolute. Cross that line, and not even light can escape. Inside, the geometry of space-time flips. Time and space trade roles. Moving forward in time now means falling inward toward a central singularity where physics, as we know it, breaks down. And yet, from the outside, nothing ever appears to fall in. It just fades, slows, reddens, and vanishes. So which version is true? Does the object fall in and hit the singularity? Or does it remain frozen on the edge of forever? The answer is both, each from its own point of view, and neither is more real than the other. This is the strange, multi-perspective nature of relativistic time. There is no single, objective truth about when something happens, only frames of reference. In one, a clock ticks normally. In another, it slows to near zero. In one, an astronaut falls through the horizon. In another, they never quite make it. Time is not universal. It is not shared. It is curved. And the deeper you go into gravity's heart, the more time stretches until it eventually seems to stop altogether. Even on Earth, this plays out. The International Space Station, orbiting far above Earth, experiences less gravity than the surface. So time moves slightly faster for astronauts aboard. If you lived your whole life there, your watch would be a tiny bit ahead of everyone on Earth when you returned. Just a fraction of a second, but enough to remind us. Our experience of time is never absolute. It is always local. Time is not a master clock ticking above the universe. It is written into the curves of space-time itself, and those curves can twist, tilt, and slow the passage of moments. So pause here. We've come far from sundials and sandglasses to clocks ticking in orbit. From the illusion of childhood summers to atomic pulses navigating continents. We've seen time slow with speed. We've seen it bend with gravity. We've watched it stretch into blackness and fold near singularities. But what if this isn't the end? What if time doesn't just bend, but sometimes disappears altogether? Because now, we cross into the quantum realm, where particles shimmer in superposition, where cause and effect blur, and where time itself might not even exist. The next chapter breaks the classical world apart. Hold tight. The illusion is about to deepen. So far, we've bent time with motion. We've warped it with gravity. We've fallen into black holes where it nearly comes to a halt. But all of this, Newton, Einstein, even GPS, still plays by the rules of classical physics. Now, we step into something stranger, smaller, less intuitive, more unreal. We're going quantum where particles don't just move through time, they break it. In classical physics, things are what they are. An object has a position, a velocity, a state, but in quantum mechanics, a particle is not in one place. It's in many places at once. It doesn't have one outcome, it has several, coexisting in a ghostly blur. This is called superposition. A particle only decides where it is when you measure it. Before that, it's not just that we don't know, it's that there is no single answer. The future hasn't happened. The past might be unsettled, and the now is a haze of probabilities. Picture Schrodinger's cat, a thought experiment, not a real one, meant to reveal the absurdity of quantum logic. You place a cat in a sealed box. Inside, a radioactive atom, a Geiger counter, a flask of poison. If the atom decays, the counter detects it. The poison is released and the cat dies. If the atom does not decay, the cat lives. Simple enough. But quantum physics says, until the box is opened, the atom is in a superposition of decayed and not decayed, which means the cat is in a superposition too, dead and alive at once. It's not just a weird metaphor. It reflects how particles behave in real labs. And here's where time begins to fray. Enter the double-slit experiment. A beam of electrons is fired at a barrier with two slits. Behind the barrier is a screen that detects where each electron lands. If you don't observe which slit the electron goes through, it behaves like a wave, interfering with itself, creating a striped pattern. But if you do observe it, even with a gentle detector, the interference vanishes. Now the electron behaves like a particle, going through one slit or the other. Your act of measurement, your choice, changes the outcome. Even more shocking? It may change the outcome of events that already happened. Welcome to the delayed choice experiment. The setup is similar. You let a particle travel toward the slits, but you wait to decide whether to measure which path it took until after it's already passed through the barrier. And depending on that choice, interference shows up or doesn't. It's as if the particle retroactively changes history based on a decision made in the future. Think about that. The present affects the past. Cause and effect begin to unravel. Time stops being a clean arrow from before to after. It becomes a tangle, a web, a loop. Then comes entanglement, perhaps the strangest feature of them all. Two particles are created in a single interaction. They fly apart to opposite ends of the galaxy, if need be, yet they remain linked. Measure the spin of one, and the spin of the other is instantly known. It's not that one influences the other, it's that they are part of the same whole, even when separated by vast distances. Einstein called it spooky action at a distance. But it's real, proven, used in quantum computers and encryption today. And here's the kicker. This entanglement doesn't care about time. It works whether you measure the first particle before or after the second. The idea of before and after loses its meaning. So what does this say about time? Maybe that we've been asking the wrong questions. Because in some theories, particularly those trying to unify quantum mechanics and gravity, time might not exist at the deepest level. Time, in these models, is not fundamental, it's emergent, a byproduct of other things like entanglement, like the relations between particles, like the flow of information. In loop quantum gravity, for instance, space and time dissolve into tiny loops, woven together. There is no now, just a web of quantum events. In the Page-Wouters model, the entire universe exists in a timeless quantum state, but subsystems inside it experience time as an illusion of entanglement with the rest. It's as if time only exists from the inside. The universe, viewed all at once, is frozen, but from within, things move. Like characters in a film who believe time is passing, while the real itself remains still. It's dizzying. We started with clocks, moved through memory, measured with atoms, broke time with speed and gravity. And now, in the quantum world, we find that time might not even be real, or at least, not as real as we thought. So where does that leave us? If time is a byproduct, then what's the cause? What's the deeper structure beneath the illusion? What is reality made of, if not space and time? Those are questions we're only beginning to ask, and they lead into the next great mystery: why time flows in one direction. Because even if time isn't fundamental, we still experience it as an arrow, from past to future, never the other way around. And that arrow holds secrets as old as the universe itself. Entropy, disorder, cosmic beginnings. That's where we go next. Everywhere you look, time moves forward. A glass shatters, smoke drifts upward, a wave crashes, then fades. You never see the reverse. You never see a broken cup leap back together. Never watch smoke spiral down into a cigarette. Never see a wave unbreak, reassembling its crest before slinking back into the sea. There's a direction to time of flow. We feel it, we live by it, and we suffer under it. This is called the arrow of time, and it's unlike anything else in physics. Because the laws of nature, Newton's, Maxwell's, Einstein's, Schrodinger's, don't actually care about direction. They work forward or backward, reverse the equations, and they still function. A movie of the universe played in reverse would still obey the math. So why, then, does reality only go one way? Why does memory point backward, while intention points forward? Why do we remember the past, but never the future? Why is there irreversibility in a universe whose rules are reversible? The answer, as far as we know, lies in one word: entropy. Entropy is a measure of disorder. More precisely, it's the number of ways a system can be arranged without changing its overall appearance. Take a deck of cards. When freshly shuffled, it looks random, but there are an astronomical number of ways that randomness can be achieved. Now sort the cards back into perfect order, ace to king, suit by suit. There is only one way to do that. So, the ordered deck is low entropy. The shuffled one is high entropy. And here's the crucial part: there are vastly more high entropy states than low entropy ones. The universe follows that tendency. It slides gently but relentlessly from order to disorder, from simple to complex, from reversible to irreversible. This is why you never see the egg uncrack, why spilled milk doesn't leap back into the glass. It's not because it's impossible. The math allows it, but the odds are infinitesimal. The number of microstates, the hidden atomic level arrangements that look like a broken egg, is astronomically larger than the number that look like a pristine one. So the universe drifts toward probability. Entropy is not just a measure of messiness. It is a measure of what is likely, and the most likely outcome is the one with the most options. That's why time has a direction, because entropy increases. That's it. That's the arrow. It's not time itself that flows, but the distribution of possibilities. Your brain, your thoughts, your memory, they are built atop entropy. To form a memory, your brain must change. Neurons must fire, patterns must lock in, energy must be spent, and that process is irreversible. It leaves a thermodynamic trace. You remember the past because entropy increased when you recorded it, but the future, it hasn't left its trace yet, so we cannot recall it, only predict, guess, or imagine. But now comes a deeper mystery. If the arrow of time is tied to entropy increasing, why did the universe start in a state of low entropy? Because that's what it must have done. The Big Bang, the earliest moment we can speak of, must have been highly ordered, an extraordinarily low entropy event. That goes against intuition. You'd think a huge explosion would be messy, but in terms of gravitational entropy, it was as smooth as it gets. Galaxies had not yet formed. Matter was evenly distributed, Space was flat. The universe was in a strange, delicate calm. Then, over time, clumps formed, structures collapsed, stars ignited, entropy began to rise. But why did it start that way? No one knows. This is sometimes called the past hypothesis, the idea that our universe simply began in an incredibly special state. But that raises more questions than it answers. Why would the universe begin in such an improbable condition? Was it a cosmic accident? The result of a multiverse where we happen to land in a low entropy bubble? Or is there a deeper law we don't yet understand? Some physicists speculate that entropy might decrease in other parts of the universe, that our arrow of time is just local. Others suggest time is symmetric, and that on the other side of the Big Bang, another universe unfolds in the opposite direction. In that mirror universe, entropy increases their way, and to them, we are the ones going backward. It's elegant, it's haunting, and we have no way yet to prove or disprove it. But for us, here, now, we live in one direction only. We are bound to the flow, from birth to death, from ignition to decay, from simplicity to complexity, and ultimately, perhaps, to silence. We build meaning in that flow. We mourn what passes. We chase what lies ahead. We make promises, raise children, tell stories, all within this thin thread we call time's arrow. It is not a law carved in stone. It is not enforced by nature's deepest symmetries. It is a drift, a tendency, a whisper of possibility rising from the statistics of the cosmos itself, and yet it defines us. So, what if this arrow breaks? What if, somewhere in the universe, time does not flow, or flows the other way, or flows in circles? What happens to cause and effect? To memory and self? What happens to us? That's where we're heading, because there is one more door to open, one more paradox to enter, and behind it lie questions we may never fully answer. Time travel, block time, and the possibility that every moment past, present, and future already exists. We've followed time like a river, felt it bend under gravity, watched it tangle in quantum uncertainty, seen it drift always forward as entropy rises. But what if that drift is not motion at all? What if past, present, and future are all equally real, already written into the fabric of the cosmos? This is the idea behind eternalism, a view of time known as the block universe. In this picture, the universe is not a film playing forward. It is the entire reel, past frames, future scenes, and every instant in between, existing together. You don't move through time. You are simply located at a particular slice within a vast, four-dimensional structure. Time becomes just another coordinate, like up, down, left, right, and in this view, the future is as fixed as the past. It sounds strange, but it's not just science fiction. It's the natural consequence of relativity, because if simultaneity is relative, if two events can happen in a different order depending on how you move, then there's no absolute now to anchor us, which means there's no objective moment where the present truly resides. Every moment is, every moment was, every moment will be, depending on where you stand. So time doesn't pass, it simply is. And you, your birth, your memories, your death, are all part of this great frozen tapestry, still changing from your perspective, but already complete from a higher view. It's a comforting and unsettling thought. Comforting because nothing is truly lost. Unsettling because nothing can be changed. Free will, in this view, may be an illusion. The future already exists. You're simply not there yet. And if that's true, what about time travel? Could we leap across this block? Skip ahead? Double back? Is the arrow of time negotiable? Let's begin with travel to the future. That part is easy because we've already done it. Every time you move quickly, every time you spend time near a gravitational well, you shift relative to someone else's clock. Astronauts aboard the International Space Station age ever so slightly slower than those on Earth. Satellites experience time differently than ground-based clocks. It's tiny microseconds. But the effect is real. With enough speed or enough gravity, you could leap years into someone else's future. So future travel? Possible, proven. But past travel is where the paradox begins. To go back in time is to risk breaking logic itself. The famous grandfather paradox asks, what if you went back and prevented your own birth? Who, then, was the you who went back? Cause and effect implode. Consistency vanishes. Reality loops on itself. To solve this, physicists have explored strange solutions, some purely theoretical, others drawn from Einstein's own equations. Among the most fascinating, closed time-like curves. These are loops in spacetime, where a particle or a person could trace a path through time that eventually leads back to their own past. The math allows it. The interpretation is up for debate. But one potential tool for creating such a loop? Wormholes. Wormholes are shortcuts through spacetime, bridges between distant points. Think of spacetime as a sheet of paper. Fold the paper so 2 points touch. Punch a hole through. That's a wormhole. General relativity permits them, but creating and stabilizing one would require exotic matter, something with negative energy density, which we've never confirmed exists in usable form. But suppose you had one, and suppose one mouth of the wormhole experienced extreme acceleration, say, a journey near the speed of light. Due to time dilation, that end would become desynchronized from the other. Enter the wormhole from one side, and you could emerge before you left. The structure becomes a loop in time, a literal time machine. It sounds like fiction, and yet the math checks out. That's why people like Kip Thorne, Nobel laureate and advisor to Interstellar, have spent serious effort exploring these ideas. But nature may have a failsafe. Stephen Hawking proposed the chronology protection conjecture, the idea that the laws of physics forbid time travel. In order to protect causality, maybe every time a paradox tries to form, the universe prevents it through radiation, instability, or breakdown of spacetime. So perhaps time loops are mathematically possible, but physically unreachable. Still, the questions remain. If the block universe is real, and the future already exists, then why can't we go there? If the past is still there, then why can't we visit it? Maybe we can't move freely, because we are embedded within time, just as a character in a painting cannot leap to another canvas. Or maybe, at the deepest level, the painting itself is still being drawn. There's a final twist. Some theories suggest that time travel doesn't need paradoxes. In a deterministic block universe, any trip to the past already happened. Any interference is already part of history. You didn't change the past, you caused it. There is no contradiction, because everything fits into a single, consistent loop. It's called the Novikov self-consistency principle. It doesn't let you do anything you want, but it does allow time travel, as long as you can't alter outcomes that were already fixed. So, perhaps every choice you make, every fork in the road, was already part of the map. Even your attempt to change the story was written into the story itself. So where does that leave us? Are we free? Are we trapped? Or is freedom just a feeling we experience? Within a world that was never really flowing, one more piece remains. A final question, so big, so strange, that it threatens to unravel the entire idea of time altogether. What if time isn't even real? What if it's not just relative, not just emergent, but illusory? That's where we go next. The deepest paradox of all. We've traveled far through the cosmos of time. We've measured it with atoms, bent it with gravity, broken it with motion, questioned it with quantum uncertainty, twisted it with wormholes and paradox. And now, we arrive at the edge of the map. Here, the question is no longer, what is time? But something stranger, something harder to face. Is time even real at all? From one point of view, time seems undeniable. We age, we remember, we act, then see consequences. We are stitched into a timeline, past behind us, future ahead. But physics whispers another possibility, that time is not fundamental, that it is not built into the fabric of the universe, but stitched into the fabric of us. That time is not something we move through, but something we construct to give shape to our experience. Consider this: in quantum mechanics, there's no built-in flow. The equations don't say which direction is forward. They describe probabilities, state vectors, wave functions. They describe what can happen, but not when or in what order it must unfold. Even in general relativity, our best description of space-time, time is just one coordinate among others. It bends, it stretches, but it doesn't tick on its own. There is no cosmic metronome, no beat that keeps the universe in rhythm. So if time doesn't flow, where does the flow come from? Maybe it comes from us, from the structure of our minds, from the way consciousness moves through physical states. We don't experience all of reality at once. We live moment by moment. Our memories reach backward. Our choices lean forward. So we assume time flows, when in truth, it may be our awareness that steps. Like the beam of a flashlight scanning a painting, we see one patch at a time, not the full canvas. But the canvas is there whole and unmoving. It never changed. We just moved across it. This is the idea behind time as an illusion. Not because it's false, but because it's constructed, like color, which is not a property of objects, but a result of how our brains process light. Time may be the same, not a thing that exists, but a sensation we've evolved to experience. And what we experience as passing time might be nothing more than this sequence of brain states. One moment leads to the next, each encoded with memory of the last. So we feel movement, but that movement may be internal, not a property of the universe, but of the observer. Some models take this even further. The Page-Wooter's framework, for instance, proposes a universe that is completely timeless, a vast, static, quantum state, no ticking clock, no beginning, no end. And yet, inside that state, observers can experience time relative to their entanglement with the rest. You don't need an external clock, just a relationship between systems. From this view, time is not global, it is relational, a story told between parts of the whole. Other models, like Julian Barber's Platonia, suggest something even more radical. That reality is not a flowing history, but a vast collection of nows, each moment frozen, complete, and eternal, not moving from one to the next, but existing all at once, like frames in an infinite library. Your sense of self, your story, your continuity, is just your brain interpreting one. Now, which happens to include memory of others. There's no actual travel, just the illusion of having come from somewhere and heading towards something else, like watching a still image that thinks it used to be another image. So what does this mean? If time isn't real, then change may be an illusion, causality may be a convenience, history may be a structure, not a journey, and our deepest intuitions about choice, growth, decay, loss may be projections, our minds cast onto a still reality. That's not to say they're meaningless, only that their meaning might be internal, not universal. You still live, still love, still change, but the direction of that change, the feeling of moving forward, might be how consciousness stitches itself into the universe. There's one more layer. Some physicists now wonder if space-time itself, not just time, might be emergent. That geometry arises from entanglement, that distance and duration are not built-in features of reality, but side effects of deeper quantum structure. Imagine that, a universe where neither space nor time are truly real, where all of physics floats atop something even more fundamental, something timeless, unchanging, pure, and we, tiny observers, embedded in complexity, see that depth as motion, see that stillness as life, see that silence as time. So, where does that leave us? Maybe with humility, maybe with wonder, because whether time is real or not, we live inside its story. We fall in love 1 second at a time. We grieve in minutes, remember in decades. We raise children, lose parents, and grow old under the slow pulse of something we might never fully understand. And yet, we try, we measure, we model, we imagine, we ask, because somewhere in that asking, we touch something real. Not time, perhaps, but something deeper. And that's where we go next. Into meaning, into being, into why it matters, that we even care about time at all. So now we return to the beginning, not just of this journey, but to the beginning of a question. What is time? After nearly 2 hours together, we've seen time as a feeling, a coordinate, a curve, a mystery. We've watched it slow near black holes, tangle in quantum paradox, and dissolve into entanglement. We've followed its arrow through entropy, then turned to see that arrow blur, bend, and possibly vanish altogether. And what we're left with is not a simple answer, but something better, a sense of wonder. Because even if time is not what we thought, even if it's not real in the way we imagined, its effects still shape every second of our lives. We feel time in our bones, in the way knees ache, in the way children grow, in the way memories soften and fade. We live inside it, or perhaps we carry it within us. And that, maybe, is the more beautiful truth. Time is not just something we observe, it's something we are. Your thoughts, built on the past, your dreams, projected into the future, your very sense of identity, woven from moments you can't revisit, but still feel echo inside you. And this gives time its power, not just as physics, but as meaning. The present is fleeting, a sliver between memory and anticipation, and yet we pour our whole lives into that sliver. A glance, a breath, a goodbye, a yes. We are fragile things. We live for only a few billion heartbeats, a few decades of sunlight, a single orbit around a quiet star, drifting in a galaxy. That itself is falling towards something larger. And yet, in that brief flicker, we ask these impossible questions. What is time? Where does it come from? Why does it flow? And the asking itself, the fact that we care, is a kind of miracle. So maybe the purpose of time is not to be understood completely. Maybe it's here to make meaning possible, because without time, there is no growth, no learning, no stories, no music. No wonder. Time is the frame that gives shape to change, and change is where all beauty lives. The falling of snow, the opening of a hand, the moment between two notes in a song, the silence that comes after I love you, each only exists because of time. And so we return to you, to the moment you're in right now. You've spent time with this story. Let it unfold at its own rhythm. Listened, felt, remembered. Maybe now you feel more curious, maybe more uncertain, or maybe just still. That's enough. That's the gift. Because if time is real, then this moment matters. And if time is not real, then this moment is all that ever was. Either way, you are here, now, alive in the mystery. And that is something to hold gently. So, take a deep breath. Feel the time that passes between inhale and exhale. That's it. That's life. It slips through your fingers, but it touches everything. Moments don't last, but they leave echoes. And in those echoes, we live on. Thank you for walking this journey, for giving your time, however you define it, to something quiet, curious, and cosmic. If this story stirred something in you, a thought, a memory, a question, carry it with you. Let it unfold, let it ripple, and maybe, in your own way, pass it on, because time may be an illusion, but wonder is always real.